we're going to talk about the union and intersection of sets. But what we're going to do is we're going to specifically talk about intervals of numbers. This is going to give us some weird cases towards the end here. So we're going to start out with and end with 4 examples, hopefully giving us all the different cases that we're going to run into. Our first example, we're going to have 2 sets, and we're going to do the OR case. This is called set builder notation. So we would say that set A is the set of all x's such that, that's what the vertical line is, x is bigger than 5. Now we have another set, set B, and set B is the set of all x's such that, there's that vertical line again, x is less than or equal to 2. Now the OR case means that we're talking about union. So we're going to go ahead and graph both A and B. And I'm going to put down both the 2 and the 5. And for set A, we are specifically x is bigger than 5. Now I'm going to have a nice big open circle, making it really clear I'm not including the endpoint 5. Set B is specifically going to be anything less than or equal to 2. So I'm going to have a nice big solid circle, shade that thing in, and anything less than. Now the OR notation means that either case could hold. I could have things less than 2, or I could have things bigger than 5. Both are true. So when I write this in interval notation, A union B, it's union because of the OR. I'm going to have anything less than 2, so parenthesis, negative infinity to 2. And I'm including the endpoint, so I got a nice solid bracket here. Union with parenthesis 5. Now note, again, I have a parenthesis because I'm not including 5. The union is sort of the part where I'm skipping over all the stuff between 2 and 5. So I only want stuff less than 2 and bigger than 5. So there's my interval notation. For my next example, we're going to handle an AND case. AND is going to mean intersection. So we're going to say that the set A is the set of all x's such that, vertical line, x is bigger than or equal to 3. And, so both conditions have to be held. So I have B here is equal to x such that x is less than or equal to 7. Again, I'm looking for overlap on my graphs here. So as I graph A is anything bigger than 3. Now I'm including it, so I have a nice solid dot there, and anything bigger is to the right. I'm going to also write down the 7. Even though I'm not going to use it on this graph, I'll use it on both graphs. So there's set A. Now set B, I like writing it this way where they're on top of each other. It's very easy to see where there's overlap or where there's no overlap. So set B, we're looking for everything less than or equal to 7. So again, I have a nice solid circle, and everything less than 7. Now because of the AND, I'm looking for overlap. So my answer, I'll go ahead and write it as a graph. Is going to be the everything between 3 and 7. The other parts where it's less than 3 or bigger than 7, that's not AND. That would be the OR case. So we're only looking for everything in between. And I'm going to go ahead and write the answer in interval notation, where A intersection B, we could say A and B would be the same thing. And I'm going to include the endpoint, so I'm going to have nice solid brackets here, 3, 7, with solid brackets. Please note the difference between these two. This is really going to matter later. Moving on to my next example. I'm going to have set A, this time, is the set of all x's, such that x is less than or equal to 0. And, so this is an and case, like the example above. Remember, and means I'm including both sets. It's got to be where they overlap. That's what and means. So I'm going to go ahead and graph out A and B separately. Where A is less than or equal to 0. Now I'm going to have a nice solid dot for the 0, because I'm including 0. And I'm going to have everything less than that, so that's going off to negative infinity there. Set B is a little different. Set B is going to be everything bigger than 2, but I'm not going to include 2. So I'm going to have a nice open circle, making it very clear that 2 is not included as an endpoint. Now, remember, and means I'm looking for overlap, and you'll note there's a big gap there between 0 and 2. There is no overlap between these two. So A intersection B, in this case, is going to be what we call the empty set, or the null set. Meaning there is no overlap, there is no and. Meaning there's no solution in this particular case. This last example is another weird case. We'll say that A is the set of all x's such that x is less than or equal to 7. In this case, or B is the set of all x's such that x is bigger than or equal to 5. Again, as a visual, what I'm going to do is I'm going to draw out A and B on a graph. I got my 5, my 7. Now set A is going to be everything less than 7. And we're including 7 because of the equal symbol, so we're going to go everything less than 7. Set B, it's going to be everything bigger than or equal to 5. So again, I'm going to have a nice solid circle. And everything bigger than. Now the OR notation, the OR means that I'm not looking for overlap, I'm just looking for anywhere that it's covered. And because in this case there is overlap, everything bigger than 5 or less than 7 is going to include everything. So A union B is going to be any real number, and we express that negative infinity to infinity. So these are the 4 basic cases here.